Hello everyone, I'm Lin Wei Chen, working in the National Grid Electricity Transmission Innovation Team. We have set up this collaborative project 02050 in 2019, together with Wales and Western Utilities, Western Power Distribution, and the National Grid Gas to develop an optimized net zero pathways for South Wales. And today I'm glad to invite our project manager Anne Cousins from ARP to quickly take you through what we have achieved so far. I will now hand over to Anne. Thank you.
Hello. Thank you so much for having me here today. It's great to be here. My name is Anne Cousins. I'm an associate specialising in energy and climate change at Arup. I'm also project manager for a project called South Wales 02050. As you can see from this slide, 02050 is a collaborative project. So our key project partners are National Grid, Wales and West and WPD. So we're very grateful to them for funding the project. We have a range of different consultants and suppliers providing technical input and evidence, as you can see here. And we have a review committee, not shown on this slide actually, chaired by Welsh Government, and we're very grateful for their input in challenging our outputs to make sure that we are providing robust and useful and relevant outputs for South Wales. As the name suggests, South Wales 02050 is about developing pathways to net zero by 2050 for the 14 local authority areas in South Wales. We're taking a whole energy systems approach, and we're looking to inform policy and investment decisions. We're looking to develop recommendations that will enable a fair transition for everyone. And we're also recognising that we are learning along the way, and we're hoping that the approach that we're taking here can help to provide a blueprint for decarbonisation planning at a local and regional level for other areas of the country. Some of the things that make this project slightly different to many other similar projects out there are, firstly, we're recognising that the future is uncertain. We know that in trying to model the future energy system in 2050, we don't know what that will look like, and we can't accurately predict. We've therefore developed socioeconomic scenarios, which each of these three scenarios might necessitate a different response from the energy system. And so we're hoping that this approach will help us to account for some of that inherent uncertainty. Our approach to modelling, secondly, which is to optimise or goal seek, looking for the lowest cost, lowest carbon mix of technologies. This is distinct from the alternative approach, which is to develop a potential mix of technologies and then model and test that. So we're hoping that this provides a more robust output. And then the third thing to mention is just the scale of the project. So by taking this slightly larger regional scale, as well as looking at a more in-depth level at 3 local authority areas, we're hoping that we're able to think slightly differently about each of the different components of the energy system. So thinking about transport between cities as well as the heat networks within cities, for example. This slightly complicated looking slide gives you an insight into some of the challenges that we've faced with this project, with lots of different input from different technical specialists. Making the connections, interdependencies and data flows clear between the teams has been one of our key challenges. And we're now at the point of beginning to have a confirmed set of inputs to our modelling, with initial results to follow in the weeks and months ahead. So a little bit earlier, I mentioned scenarios. These are the 3 socioeconomic scenarios that we've developed, and we've considered how the energy demand might be different under each of the 3 scenarios. We've also developed a socioeconomic baseline looking at factors such as GDP and fuel poverty, and we'll be looking to assess the socioeconomic impact and opportunities emerging from our technical outputs in due course. This next slide just gives you an overview of where the project is up to. On slide 4, you saw each of the different work packages, and many of those have now concluded. So we've completed our analysis for the decarbonisation of heat, of transport, industry, and energy generation sectors. As I mentioned, we've got the socioeconomic impact analysis framework, and our optimisation analysis is underway, looking to help us design the most cost-effective pathways, looking at those pathways, looking at the timestamps of 2030, 2040 and 2050 to help us see the optimal pathways through this and deliver no regret solutions. We're looking to publish our final report and recommendations in February next year, so do look out for that in due course. As our optimisation is still underway, these graphs on this emerging findings slide are deliberately small and illegible because these are just indicative results rather than actual results at this stage. But they give you an indication of the type of output that we'll get. So we'll get an optimized mix of generation to meet hourly demand. And as I said, looking at this across 10 yearly timestamps to help us see those optimal pathways and think about the no regret solutions. What can we do now that we know will be needed in each of those 3 timestamps? I thought it was just useful, whilst this project is by no means complete. We've been going for some time now and have identified a number of different challenges that we will continue to debate and will continue to evolve over time. And I thought I'd just share some of those with you now. So first up, we've been taking an approach to modelling the lowest cost solutions across the whole energy system. And we know that costs and benefits aren't allocated in this way. So understanding and working out how best to share those costs and benefits will be really important in order to achieve that objective of a just transition. We began this project and thinking about the transport demand in the future before COVID, if you can even remember that time when we weren't all locked in our homes. And there remains a lot of uncertainty following this period of time as to how the future of transport might change in a post-COVID world. And last but not least, we've been exploring the role of South Wales in the wider UK energy system. At the moment, we know that South Wales is a net exporter of energy, and our approach to islanding and demonstrating the interconnections between South Wales and the UK energy system has been complex, and we're still exploring whether export needs to remain an ambition for South Wales into the future. I will leave this presentation there, but do look out for our report in February next year. And we look forward to hearing your feedback. Thank you very much.
Hello everyone, I'm Lin Wei Chen, working in the National Grid Electricity Transmission Innovation Team. We have set up the multi-vector modeling project with Manchester University to look at the impact of heat and transport decarbonisation on our networks. And today I'm glad to invite the research team to present the outcomes we made through the project. I will now hand over to Alex and Asad from the Manchester University. Thank you.
Thank you for the introduction. My name is Alejandro Martinez, or simply Alex, and I'm an academic at the University of Manchester. In this presentation, we will discuss the latest findings of this project, which is led by me and my colleagues and partners named on screen. I will be delivering the first part of this presentation, and my colleague Asad will deliver the second half. Before we begin, it's worth highlighting three key aspects of this project, which will be addressed in this presentation. Firstly, as mentioned by Lingwei, this project aims to investigate the impacts on the power network of different heat and transport decarbonization pathways. For example, the future energy scenarios FES. Secondly, this is not a straightforward process, as the pathways are constantly changing. Thus, rather than producing a single study for the existing pathways, our objective is to develop a flexible open access tool which can be used to investigate emerging pathways and support the development of new ones. Thirdly, the proposed tool, which brings together top-down targets and bottom-up modeling, produces energy data with high temporal and spatial resolution, which will be demonstrated with applications to Greater Manchester. Let us begin with the motivation for this work. Why do we need another project on decarbonization pathways? Well, we know that there are ongoing efforts to plan for a net zero carbon future. This includes, for example, the work by the Committee of Climate Change and the development of FES, among other important work. These pieces of work aim to identify economically attractive plans to decarbonize our energy use using a whole system perspective. That is, we recognize that we have to consider a wide range of technologies across heating, transports, cooking, distributed generation, as well as multiple energy vectors, such as electricity, heat, gas, hydrogen, etc. Our project builds on these pieces of work, but instead of only focusing on the generation of net zero energy, we also explore the impacts on the power network, which has to transport all these energies. That is, we investigate the network impacts associated with low carbon technologies by developing energy data with high spatial and temporal resolution. This data allows planners to identify potential bottlenecks and network reinforcement needs. And in order to produce data with the required temporal and spatial resolution, we have proposed a tool that brings together top-down decarbonization targets with bottom-up modeling of individual technologies for heating and transports. The tool includes multiple models which use network information and historical energy consumption and temperatures and other data as a means to model decarbonization pathways. As shown here, each component of the proposed tool involves a wide range of detailed models. For example, the tool allows defining multiple heating technologies which can use different vectors, including hydrogen, electricity, or other customized vectors, and also allows us to customize the operation and sizing of the devices. My colleague Asad will address this further. Ultimately, we combine all these different models to produce energy profiles for representative years and peak 1 in 20 conditions, which are modeled with half-hourly resolution at the primary, BSP, and GSP levels. I will now hand over to Asad, who will present the second half of this presentation.
Thank you, Alex. I will first introduce the multi-vector energy integration tool, along with its main features, and then its application in the context of Greater Manchester. This tool uses the above-mentioned methodology and first calculates the energy demand profiles for each type of consumers, then aggregates for the number of buildings or transport vehicles in each postcode, and results are calculated at a primary substation level. The heating profiles are modeled for the domestic, commercial, and industrial consumers, where there are separate profiles for the building such as flats, terraced houses, semi-detached, and detached houses. The tool also considers the effect of improvement in thermal insulation, being good, medium, and poor, and assumes improvement in insulation is aligned with the amount of electrification. For transport profiles, the electric vehicle profiles are modeled with both slow and rapid charging options. It is worth highlighting that this tool is available as an executable file, and it is possible for the transmission and distribution network operator to make changes in its source code, but will require MATLAB software license. The tool allows user with the flexibility to define custom heating technologies and control parameters using an Excel spreadsheet. These settings include energy vectors, custom definition of efficiency, rules for sizing and operation of different heating technologies, for example, heat pumps, resistive heating, etc. Define baseline conditions and target technology mix, and even modification of parameters such as percentage of electrification, sensitivity, population, and demand growth. Now this slide shows the summary of customization features that adds flexibility to the tool. The first column of the spreadsheet contains the list of technologies. The second column provides the flexibility to assign whether a technology is connected to a district heating network or not. If it is, then the tool will search for regions with high annual heat demand density and consider that technology only if the postcodes are feasible for the district heating network. The third, fourth, and fifth columns are the most important ones. The efficiency column enables the user to define additional energy vectors along with their efficiency. The sizing column sets rules for the capacity of each technology. The capacities can be sized either at a typical year or 1 in 20 peak year, or even user-defined minimum design temperature. Additionally, the tool calculates the sizing separately for each technology. This is helpful if one technology needs to be sized at a typical peak year, while other at a 1 in 20 peak, as shown in this example here. The operational column deals with the definition of backup technologies for the unfulfilled heat demand. This is particularly useful when the extreme events are to be modeled, or the technology capacity is undersized, and the preferred backup technology can be provided in the column named Technology Backup Technology, along with its share in the adjacent column. As mentioned earlier, that it is a complex and challenging task, which is evident from a limited number of parameters shown here. The Excel sheet contains more parameters. Now I will move to the next part of my presentation. This is the National Grid has recently published future energy scenarios. Now the future energy scenarios for 2020 provides 4 pathways, and among these, 3 are set to achieve net zero emission targets. These scenarios provide a detailed technical and economical feasible plan to achieve net zero emissions by year 2050. The share of each technology is shown in this figure. Here, these pathways are used to investigate the electricity demand requirements with the decarbonisation of heating network in Greater Manchester by 2050. Now this slide shows the geographical distribution of 188 primary substations in Greater Manchester, which are investigated using this tool. Only one of the substation is selected as a representative example to show comparison between the heat demand profile in the following figures. Now in the next slide, the data shows that the comparison of operational electricity demand profiles among different future energy scenarios. While comparing results for year 2050, the consumer transformation scenario has the highest amount of electrification compared to other net zero scenarios, and the peak electricity power demand increases up to 25 megawatt compared to the demand of 7.2 megawatt with current mix of heating technologies. This suggests that the electricity demand in the future net zero pathway depends on the availability of hydrogen and number of air source heat pump installations. Now, the breakdown of electricity power profile among different technologies elaborates that in steady progression scenario, the share of electricity power demand is mainly dominated by resistive heating and electric storage. However, in future this will change, and the electricity demand trend will follow consumer behavior with the increased number of air source heat pump installations. As shown here in the consumer transformation scenario, the demand has two peaks, one in the morning and other in the evening. This highlights the need for future demand side management analysis to mitigate these peaks. Besides these analyses, the tool has a capability to challenge existing design practices. To this end, a sensitivity analysis has been performed to investigate the electricity demand of a air source heat pump with varying design outdoor air temperatures on the same region discussed above. The air source heat pumps are considered as a primary heating source with a share of 100%, and resistive heating is considered as a backup technology for extreme events. The data in this figure shows that the electricity power demand increases exponentially once the temperature drops below -4 degrees centigrade. This is due to resistive heating, which acts as a backup heating source. This suggests that the air source heat pumps should be designed at lower outdoor temperatures, as this reduces the electricity demand from the electrical grid. Now, if I summarize everything and conclude, firstly, we have concluded the energy demand of a future net zero electrical grid depends on the availability of hydrogen and amount of air source heat pump installations. Secondly, in future, with the electrification of heating sector, the electricity demand trend will follow consumer behavior. Thirdly, the air source heat pump should be designed at lower outdoor temperature, as this reduces the electricity demand from the electrical grid. Finally, this open access multi-vector energy tool can support TNOs or DNOs to investigate the impact on energy infrastructure and requirements in various future multi-energy decarbonization pathways. As I mentioned earlier, that this tool is still under development. The next steps includes investigation of different technologies and scenarios, and even variations of future energy scenarios, and further development of the tool, for example, to better integrate transport modeling, energy efficiency, and other things. Now, if you need more information, then in the next slide, there are the more contact details for the researchers. You can contact this team. And finally, we have already also published some of our research work, which is available in this slide. Please refer them. Thank you for your time.
Well, that brings us to the close of ENIC 2020. I'd like to thank all of our session speakers and also all of you who have come along and participated in today's event. It's been a pleasure hosting this session for you. I hope you've enjoyed it as much as I have. For the next 40 days, all of the content from our conference sessions will be available on demand through this platform, as will the content on each of the exhibition stands. So please feel free to visit again if there's anything that you have missed. That's it from me for now. Take care, and I look forward to seeing you at next year's ENIC 2021. Thank you.